Sinusoidal oscillators. An oscillator is a circuit which produces periodic AC signals with the prescribed properties like waveform, frequency, and amplitude. In an amplifier, an AC input is amplified to an AC output with a DC controlled input. But in an oscillator, a DC power input is converted to AC output without having an AC input. Sinusoidal oscillators are oscillators which produce an output having sine waveform. They are called sinusoidal or harmonic oscillators. They can produce a frequency ranging from 20 Hz to 1 GHz. Non-sinusoidal oscillators produces square wave, rectangular or sawtooth waveforms. They are also known as relaxation oscillators. They can produce frequencies ranging from 0 Hz to 20 MHz. Now we are discussing only about sinusoidal oscillators. Tuned circuit oscillators. These oscillators use tuned circuit consisting of inductor and capacitor to generate high frequency signals. Therefore, they are known as high frequency or radio frequency oscillators. For example, Hartley, Colpitts, clap oscillators. In RC oscillators, they use resistor and capacitors to generate low or audio frequency signals. They are known as audio frequency oscillators or AF oscillators. For example, phase shift and wien bridge oscillators. Crystal oscillators use quartz crystals to generate highly stabilized output signal with frequencies up to 10 MHz. For example, piezo oscillator. Negative resistance oscillator use negative resistance characteristic of the device such as tunnel device. For example, tuned diode oscillator. There are two types of sinusoidal oscillations, damped oscillation and undamped oscillation. In a damped oscillation, the amplitude goes on decreasing with time. But in undamped oscillation, the amplitude remains constant with time. The essential part of an oscillator is the oscillatory circuit. A circuit which produces electrical oscillation of any desired frequency is known as oscillatory circuit or tank circuit. A simple oscillatory circuit consists of capacitor and inductor in parallel. Suppose the capacitor is charged from a DC device with a polarity like this. The upper plate of capacitor has deficit of electrons and lower plate has excess of electrons. Therefore, there is voltage across the capacitor and the capacitor has electrostatic energy. When the switch S is closed, the capacitor will discharge through the inductor in this direction. The current flow sets up magnetic field around the coil. Due to inductive effect, the current builds up slowly towards maximum value. The circuit current will be maximum when the capacitor is fully discharged. At that instant, electrostatic energy is zero, but because electron motion is great, the magnetic field energy around the coil is maximum. Thus, the electrostatic energy across the capacitor is completely converted into magnetic field around the coil. Once the capacitor is discharged, the magnetic field will begin to collapse and produce a counter EMF. According to Lenz's law, the counter EMF will keep current flowing in the same direction. The result is that capacitor is now charged in opposite polarity, making upper plate negative and lower plate positive. After the collapsing of the field, now again the capacitor discharges through the coil in this direction and magnetic field arises around the coil and the magnetic field becomes maximum when the capacitor discharges fully. The sequence of charge and discharge results in alternating motion of electrons or an oscillating current. The energy is alternately stored in electric field of the capacitor and the magnetic field of the inductance coil. The interchange of energy between L and C repeated over and again, resulting in producing of oscillation. The frequency of oscillation is given by F is equal to 1 by 2 pi root LC. In practical tank circuit, there are resistive and radiation losses in the coil and dielectric losses in the capacitor. During each cycle, a small part of original energy is used to overcome these losses. Thus, the amplitude of oscillation is decreasing. In order to make the oscillation undamped, the amount of energy supplied should be enough to meet the losses in the tank circuit and the AC energy removed from the circuit by the load. The applied energy should have the same frequency as that of the oscillation in the tank circuit. The applied energy should be in phase with the oscillations set up in the tank circuit. A practical oscillator consists of tank circuit, amplifier and feedback network. Positive feedback amplifier. An amplifier with the proper positive feedback can can act as an oscillator. The amplifier amplifies the input signal Vi into A times Vi. A portion of the output is fed back to the input by a feedback factor beta. Therefore, Vf is equal to beta times A into Vi. If Vi is equal to Vf, we can have a faithful oscillation. For that, beta A equals 1. Beta is known as loop gain. Barkhausen criterions are set of conditions for sustained oscillations. The loop gain is equal to unity in absolute magnitude, that is modulus beta A equal to 1. The phase shift around the loop is 0 or an integer multiple of 2 pi, that is phase shift to beta A is equal to 2 pi n, where n is 0, 1, 2, etc. Voltage gain of positive feedback amplifier is A by 1 minus beta A. If beta A is equal to 1, AF tends to infinity. It means once the circuit receives the input trigger, it would become an oscillator generating oscillation with no external signal source. There are different types of transistor oscillators exist. Tuned collector oscillator. In tuned collector oscillator, the tank circuit consists of a transformer and a capacitor connected in the collector of the transistor. When the switch S is closed, the collector current starts and the capacitor charged to maximum and then discharges through the coil L1. This makes an oscillation of frequency F is equal to 1 by 2 pi root L1 C1. The oscillation induces some voltage in coil L2 by mutual induction. The frequency of voltage in coil L2 is same as that of L1, but the magnitude depends on coupling between L1 and L2 and the number of turns in L2. The voltage across L2 applies in the base emitter of the transistor and reaches the collector in the amplified form. The transformer gives a phase shift of 180 degree and an additional phase shift of 180 degree is provided by the transistor in CE mode. Thus, a total phase shift of 360 degree or 0 degree is occurs. As a result, the energy fed back to the tank circuit is in phase with the generated oscillations. Tuned collector oscillators are widely used as local oscillators in radio receivers. Colpitts oscillator. It is a transistor LC oscillator where the tank circuit consists of inductor L is connected in parallel to serial combination of capacitors C1 and C2. This RF choke is used to give easy path for DC and obstruct AC signals. When the circuit is turned on, the capacitors C1 and C2 are charged. The capacitors discharge through L and setting up oscillation of frequency F is equal to 1 by 2 pi root LC, where C is C1 C2 by C1 plus C2. The output voltage is the voltage across C1 and the feedback voltage is voltage across C2. The voltage across C1 and C2 have a phase shift of 180 degree. The voltage fed back to the transistor provides a positive feedback. A phase shift of 180 degree is provided by C1 C2 voltage divider and a further phase shift of 180 degree is provided by a transistor. In this way, feedback is properly phased to produce continuous undamped oscillations. Thus, the feedback factor beta is equal to Vf by Vo, where Vo is the voltage developed across C1 and Vf is the voltage developed across C2. Thus, beta is equal to C1 by C2. Colpitts oscillators are used in high frequency sine wave generators, local oscillator in radio receivers, RF oscillator, and in mobile applications, surface acoustical wave resonators, and in sensors. Hartley oscillator. It is a transistor LC oscillator where the tank circuit has a capacitor connected in parallel to serially connected inductors. When the circuit is turned on, the capacitor is charged. When this capacitor is fully charged, it discharges through L1 and L2 that set up an oscillation of frequency F is equal to 1 by 2 pi LC, where L is equal to L1 plus L2 plus 2M. M is the mutual inductance between L1 and L2. Here the output voltage across L1 and feedback across L2. This connection gives a phase shift of 180 degree. The voltage feedback to the transistor provides positive feedback. Thus, a phase shift of 180 degree by L1 and L2 and a further phase shift of 180 degree is provided by transistor. Thus, feedback is properly phased to produce continuous and damped oscillations. Feedback factor beta is equal to Vf by Vo, where Vo is the voltage across L1 and Vf is voltage developed across L2. Thus, beta is equal to L2 by L1. Hartley oscillator is used to produce sine wave of desired frequency, as local oscillator in radio receivers, and as RF oscillator. Phase shift oscillator. A phase shift oscillator produces sine wave using RC phase shift network. In LC tank circuits, they suffer from frequency instability and pure waveform, and they cannot be used for very low frequencies because they become too much bulky and expensive. In phase shift oscillator, it uses an RC phase shift network to produce oscillations and sufficient phase difference. In this phase shift oscillator, it uses 3 RC network. Suppose E0 is the input voltage and E0 prime is the voltage developed across the resistor R. We know that the alternating voltage E0 prime across R leads the applied voltage E0 by 5 degree. The value of phi, phase shift phi, depends on R and C. In this circuit, each RC network provides a phase shift of 60 degree, so that a total phase shift of 180 degree. When the circuit is switched on, it produces oscillation of frequency f is equal to 1 by 2 pi RC into root 6. Thus, this network provides a 180 degree phase shift and the transistor provides 180 degree phase shift, so that a 360 degree of phase shift and makes continuous and damped oscillation. And its feedback fraction is EI by E0. Phase shift oscillator does not require transformer or inductors. It can be used to produce very low frequencies. The circuit provides good frequency stability. But starting the oscillation is difficult as the feedback is generally small. The circuit gives small output. Wien bridge oscillator. The type of phase shift oscillator which is based upon Wien bridge network comprising of 4 amps connected in a bridge fashion. Here 2 amps are fully resistive and the other 2 are an RC combination. This is actually a high pass filter and this is a low pass filter, and here uses 2 transistors. Each transistor provides 180 degree phase difference, so in total a phase difference of 360 degree. This makes proper positive feedback and continuous and damped oscillation. It gives a frequency f is equal to 1 by 2 pi root R1 C1 into R2 C2. If R1 equal to R2 is equal to R and C1 equal to C2 equal to C, then f is equal to 1 by 2 pi RC. Wien bridge oscillator gives constant output. It works quite easily. Overall gain is high because of 2 transistors. The frequency of oscillation can be changed very easily, but it cannot generate very high frequencies. It requires 2 transistors and a large number of components. Crystal oscillator. A crystal oscillator is basically a tuned circuit oscillator using piezoelectric crystal as resonant tank circuit. The piezoelectric crystals, for example quartz, tourmaline, rochelle, is suitably cut and mounted between 2 metallic plates. Crystal oscillators are used whenever great stability is required, such as in communication transmitters and receivers. Normally quartz is used because it is inexpensive and naturally available and mechanically strong when compared with the other crystals. Quartz crystal exhibits piezoelectric effect. It is the property that when mechanical stress is applied across one set of its faces, a difference of potential develops across the opposite faces. Similarly, a voltage applied across one set of faces of the crystal causes mechanical distortion in the crystal shape. Electrical equivalent circuit. We can represent the crystal action by this electrical resonance circuit, RLC and CM. The circuit have 2 resonant frequencies: series resonance when RLC legs are equal, and parallel resonance or anti-resonance when the reactance of the series resonant leg equals the reactance of the capacitor CM. The impedance versus frequency plot of the crystal crystal shows two frequencies F1 and F2, the series resonance and parallel resonance. In series resonance, the impedance is minimum, and in parallel resonance, the impedance is maximum. Thus, the circuit must be connected in the series resonant operating mode for low impedance and anti-resonant operating mode for high impedance. Series resonant circuit. At the series resonant frequency of the crystal, its impedance is smallest and the amount of feedback is largest. Thus, the crystal is connected between the collector and base of the transistor. Series resonant frequency Fs is 1 by 2 pi root Lc. Parallel resonance circuit. At the parallel resonant frequency of the crystal, its impedance is highest and thus feedback will be the least. Thus, the crystal is connected at the output. It is almost similar as our Colpitts oscillator. The parallel resonant frequency Fp is 1 by 2 pi root L into C into Cm by C plus Cm. Advantages of crystal oscillator: they have high order of frequency stability. The quality factor of crystal is very high, almost 10 raised to 6, but they are fragile and can be used in low power circuits. The frequency of oscillations cannot be changed appreciably.